Welcome back to Office Hours with Dr. Clark. So today we are going to be looking, or this recording, we're going to be looking at cyclic structures. So cyclic alkanes. So cyclic alkanes, you have your cyclopropane, cyclobutane, cyclopentane, and we have cyclohexane, and we could keep going. Right. And then you have, you could put branches on the various, substituents, put a methyl, for example. So, so we'll deal with naming cyclics in a different video. So for now, we want to center cyclohexane. It's in the planar form as we show here, we have it's not very stable because the bonds in the planar form, the hydrogen bonds, well, the bonds to the hydrogen, because saying hydrogen bonds implies something totally different. So these hydrogens here, they are eclipsed with each other. Right? And it's kind of hard to see when you draw it on paper, but if you were to construct a model, you will see that all these bonds are eclipsed. CH bonds. That's in a planar form. So there's a form of cyclohexane that is very stable. It's called a chair. So now students always struggle with drawing chairs, and us teachers were always trying to get them to draw proper chairs. So if you just draw one line like that, another line like that, it made them, a little longer. And then we just do some lines to connect. I don't like how that last one looks. So now I gotta do my whole thing over. How to erase as a piece. Okay. So one line like that, or two lines right there. Okay. And then just, connect. Now we have a good looking chair. See that? So now on the chair, so actually to back up for a second, with rings, especially these smaller ones like cyclopropane cycle, there's something called ring string. Ring string. So ring string, you have a combination of torsional string and angle string. Angle string. So angle strain essentially is compressed sp3 tetrahedral angles. So the tetrahedral angle, if you recall, is 109.5 degrees, but there's no way, for example, in cyclopropane, that the bond angle between these two bonds is 109.5. It's more closer to 60. So there's repulsion that happens there, angle strain. Now, cyclohexane in this format alleviates ring strain completely. We have our tetrahedral. Now, that's based on how we draw the chair. It doesn't look like it's 109.5, but it actually is. So we have our 109.5. We have no torsional strain in the ring. So now with these cyclohexane rings, we have to differentiate between the substituents that are axial, and those are perpendicular to the axis of the ring. So if you draw your ring, any point that kind of points upwards, like that point, that point, the axis is going to be going up. If it points downward, axis is going down. So up, down, up, down. Now there's also equatorial substituents. So let's call these hydrogens. They could be something else. It could be metals, hydroxides, chlorines, ethyls. We'll call them hydrogen for now. So then there are also equatorial hydrogens. So on the points that are going up, the equatorial is angled slightly down. It's just slightly. So that's what I call equatorial. It's kind of like coming off of like on an angle horizontally. If it's pointed up, I'm sorry, if there's a down, the carbon is pointed down here, the your equatorial is angled up. This one's angled up, so my equatorial is angled down. This one is angled down, equatorial is angled up. This one's angled up, so my equatorial is angled down. This one is angled down, so my equatorial is angled up. So you see with your equatorials, you want your equatorial bond here to be parallel to this one or this bond here. So you notice that the H is parallel there. This one is parallel to this one, as well as this one here. The bonds. That's when you know you're drawing good equatorials. When you're drawing them, they're parallel to one of the carbon-carbon bonds, like the one ahead, like this one here, or the one behind it here. Likewise, this one parallel to that one, parallel to that one, this one parallel to that one, parallel to that one, this one parallel to that one, parallel to that one, right? So I know my equatorials are looking nice. You don't want to draw equatorials, for example, so here's a chair. That's not a good looking chair. So let me just follow. So so you have to make sure when you're drawing them, your your lines here are parallel. Otherwise, you're gonna get some wonky looking chairs. I have to draw mine just a little closer here. So when I do my connection, all right, so yeah, my connection here isn't that great. Okay, there we go. You see, you don't want equatorials looking like this. All right. You want to make sure equatorials are angled. So this one should be angled down. This one should be angled up. That's why it's important to draw good looking chairs. Otherwise, when you're trying to fill in your axial equatorial, they're not going to look proper. So now with chairs, the rings can do what we call ring flip. Right? There's a chair. I can have rotation of the carbon-carbon bonds, not complete rotation. Remember, rings can't fully rotate, right? Only partial rotation. So if I do some rotation, I'm going to end up with what we call the ring flip version. If I leave this carbons one, two, three, four, five, and six. My ring flip, this is carbon one. Actually, I don't like how that ring looks. See, I'm very critical about my own rings. So I always make sure my students are drawing rings that look decent. So now this is carbon one. That's two, three, five, six. So notice carbon one was pointing up, now it's pointing down. So on ring flips, whatever is axial, let's say this is a metal, it's not going to be equatorial. Okay. Whatever is equatorial is now going to be axial. And vice versa. So when this ring flips back, it's gonna go back to being axial is metal, and the H is gonna go back to being equatorial. So when you have, so this ring flip can happen. It happens at room temperature very quickly, around 25 degrees. At lower temperatures, it's a little slower. So you can actually distinguish between the two ring forms. So ring flip is not, we didn't flip the ring over, like a pancake, right? We did some gentle rotations that got us to the different ring form, right? So it looks like a mirror image, but it's not a mirror image. It's just how the rotation, happened. So think about rings, and I'm gonna diverge for a second. Let's draw the planar form. It's easier when you're trying to explain things. If I have two metal groups that are wedges, and then I have one that's a dash, one that's a wedge, do you think these are the same compound? Or do you say these are equal? Can I just kind of, rotate a little bit different one to another? They are not. So this is a cis, and this is a trans. So with rings, I cannot rotate from a cis to a trans. I have two different compounds. So we call these stereoisomers, which is a whole nother video by itself, stereoisomers. And this specific one here is in geometric. Cis trans are called geometric isomers. That's what I'm pointing out. So now let's talk about ring stability when it comes to substituents. So let's say I have, I'm gonna draw my ring, and I have a methyl group here. Now on the ring flip, my methyl group is going to be equatorial. So A versus B. Now, which one is the most stable? Would you guess? Yeah, A is less stable, B is more stable. The reason why A is less stable is because you have these hydrogens right here. So let me draw in my H's for my methyl. So these H's are interacting with the hydrogens that are those axial hydrogens. Let's call it 1. This is 2 carbons away. So it's either 1, 2, 3 this direction or 1, 2, 3 that direction. So we call that 1, 3 diaxial strain. And it's a steric strain. That happens with axial hydrogens when there's an axial substituent like a methyl, something bulky like a methyl, tert butyl, ethyl. If it's like a chlorine, it's not as drastic. Still, a little more interaction than you'd find with, if it was a hydrogen here. But definitely when you have methyls, alkyl groups, you definitely see a pronounced stability difference. So now my ring flip arrows, I can draw them longer strand going to the ring flip that has the methyl group equatorial. because there is no steric strain here. So when we're looking at substituents, rings of substituents, and we're asked, oh, draw the most stable substituent. Like, for example, I was given um, this ring. So when we give it to you in the planar form, we put some wedges and dashes. So the wedge means the substituent is angled down. So it could be equatorial down or axial down. If it's a wedge, it means it's angled up, equatorial up or axial up. So I'm going to draw I'm going to draw my ring, and I'm going to also draw the ring flipped. That's right away. So I'm going to carbon one, carbon two. Either one could be carbon one because they're both methyls. So I'm going to write on here. So carbon one, carbon two. So I'm going to put this. So carbon one is supposed to be angled down, so it can't be axial because it's the carbon is kind of pointing upwards, and the axial is not going down, it's going up at that carbon. So I'm going to put my methyl group equatorial and have it angled down in keeping with the dash. And then on carbon two, this axial, I'm sorry, this substituent, the methyl substituent is a wedge, so that means it's going upwards. So I can't do axial up here because that carbon is pointing down. So it has to be equatorial up. And this is a hydrogen here. And then you have a hydrogen going down. So now let's look at our ring flip. So if you call this carbon one, let's call it carbon two, carbon one, carbon two. So now this carbon one, since that's equatorial down, it's going to be axial down. And then carbon two, since it's equatorial up, it's going to be axial up. A, B. So which is more stable? Correct, it's going to be A, because A, both my substituents are equatorial. Stable. Both substituents are equatorial, whereas on the ring flip, so I'm gonna have a longer stick on there, a short on there. Ring flip, both substituents are axial. So not stable at all. So let's try another one. Let's try one more. So let's say I'm gonna make both of them wedges. Okay. I'm gonna draw mine. And then I like to draw my ring flip. So that I'm ready to go. So carbon one, carbon two, both going up, so it's gonna be axial or equatorial up. So carbon one, carbon two, carbon one, carbon two. So up, and then this one is gonna be equatorial up. Carbon one, equatorial up, carbon two, axial up. So A, B. So it either these rings more stable than the other? What do you think? No, both are equally stable. They both have one axial substituent and one equatorial substituent. So equally stable. So with rings, We will typically give you the planar version, and we'll give you some wedges and dashes and tell you we'll convert that to a chair and indicate which is more stable. And then you have to draw your chair and then draw the substituents based on information. Remember, dashes going down, wedges going up, and draw them appropriately, whether axial, or equatorial. And some cases, you can't help but make the group axial, for example. And then other cases, the equatorial, you can actually make the groups equatorial and it will be more stable. So we talked about that, talked about diaxial strain and how we want to substituents to be equatorial because when they're axial, there's a diaxial strain from those neighboring hydrogens that are also axial. We talked about the fact that there is stereoisomers with rings that are substituted. Now, keep in mind that the substituents have to be on different carbons for us to have cis and trans. There is no cis and trans on the same if they're connected to the same carbon. Right? So neither cis nor trans. They're connected to the same carbon. We talked about how to do ring flip and how the groups change orientation. We talked about angle strain, torsional strain, so that rings can have angle strain because of compressed bond angles. And then we also talked about Newman projections. Well, actually, that was an earlier video. So this video, we just talked about rings. All right. So that's it for our cyclohexane rings. That's the rings that we really focus on organic chemistry as far as the different conformations. All right. Join us next time for Office Hours with Dr. Clark.